In this example, we have 5 different ropes, ropes A through E, and each rope, 4 different tests were conducted to figure out its breaking strength. We want to use a single factor analysis of variance to figure out if the mean breaking strength of any of the 5 ropes is different from one another. Before conducting any statistical test, always examine your data graphically. To do this in Excel, we'll select all of our data, and I'll go Insert a Line Graph, and the original graph, so it'll plot ropes A through E, and it'll plot the 4 measurements for all 5 of those ropes. And the original graph is pretty lousy looking, pretty crappy. So I've cleaned it up by including the axis labels of breaking strength with units in pounds on the vertical axis, and then the rope type on the x-axis, ropes A through E. With an analysis of variance, what we're trying to determine is whether or not the data points for all 5 of the rope types come from a normal distribution with a population mean that's the same. In other words, I've got my population means for ropes A through E. We're trying to figure out if the data points measured for all 5 of these ropes come from normal distributions with the same population mean. And while it is true that this is possible for our case, that all 5 of the ropes came from the same normal distribution with the same population mean, it looks to be fairly unlikely. For example, for rope D, although it is possible that these 4 data points could have been collected at the low end of the normal distribution for rope D, and for rope C, these 4 data points could be here, and for rope A and rope B, it is possible that this would occur. However, it would be highly unlikely that these data points would be collected at the low end of the populations for both ropes C and D. When we run the analysis of variance, there's a high probability that we could reject the null hypothesis that the breaking strength for all 5 ropes is the same. What is likely to occur is that we'll get a relatively low p-value for this analysis, indicating that at least one of the population means is different from the other. So I'll move the chart out of the way to run the analysis. One thing you'll want to make sure that under Data that you've got the Data Analysis Tools. If you don't have it, do a search for the Data Analysis package for Excel and how to activate it. So click Data Analysis. In the following window will appear. We want ANOVA single factor selected. So with that selected, click OK. And it will ask us the input range for the single factor ANOVA. So for the input range with this highlighted, select all of the data with the labels in the top row. So we're going to group all our data grouped by columns, so rope A through E, each one has its own column, and we've got the labels being rope A through E in the first row, so make sure that's selected. And if we want to use the default value of alpha for 0.05, just leave it as is. In the output range, you could either output this as a new worksheet or a new workbook, but usually it seems to be easiest to select an output range on the same worksheet. So here I'll select an output range that starts out at I1. I'm just giving it a clear area to work with, and then I'll click OK on that. And the ANOVA table is shown here, so I'll select all of these, double click it to expand the columns. It just makes it a little bit easier to see all of the data. So I've got ropes A through E, my analysis of variance table shown here, and usually what I find most useful is the p-value. And in this case, we find a p-value of 0.00076, which is a great deal less than our alpha of 0.05. And this gives us a good indication that we could reject the null hypothesis. And it gives us a good indication that at least one of the population means is different from the other. And we will look at the data graphically. It does appear that ropes C and D are weaker than ropes A, B, and E. And this is what is causing this relatively low p-value.